Hello, this is Alan Elliott, and this is SAS Essentials Mastering SAS for Data Analytics, 3rd edition. This is Chapter 14, Analysis of Variance. In this chapter, we're going to be able to compare 3 or more means using a one-way ANOVA with multiple comparisons. Also, we'll be able to perform a repeated measures dependent samples analysis of variance, also with multiple comparisons, and to be able to graph mean comparisons. As usual, if you'd like to follow along with the examples, please download the files at this location. Let's get started. This chapter illustrates how to perform an analysis of variance, or ANOVA, for several common designs. The book covers actually 3 SAS procedures: PROC ANOVA, PROC GLM, and PROC Mixed, although PROC Mixed is covered in Chapter 14. In this chapter, we're going to be looking first at PROC ANOVA, which is a basic procedure useful for one-way ANOVA or for multi-way factorial designs with fixed factors and an equal number of observations per cell, and PROC GLM for one-way repeated measures analysis and techniques not supported by PROC ANOVA. So let's look at section 14.1, comparing 3 or more means using one-way analysis of variance. Now previously, using a t-test, we compared 2 means at a time, but when you have 3 or more means, then you move from a t-test into an analysis of variance. So a one-way ANOVA is an extension of the independent group t-test, where there are more than 2 groups. The assumptions for these are similar to that of the t-test. First, the data within groups are normally distributed with equal variances across groups, and the groups are from independent samples. That is, if you have 3 groups, group 1, 2, 3, they all contain different people, they're different subjects or different entities that you've measured. They're not unrelated. So the hypotheses for the comparison of independent groups are as followed, where k is the number of groups. The null hypothesis would be that all k means are equal, and the alternative hypothesis is that at least one comparison, or at least 2 means are not equal. All right, let's look at the simplified syntax for PROC ANOVA. It begins like most procedures in SAS, PROC ANOVA, followed by some options that we'll talk about in a minute. But then we have the class statement. The class statement defines the grouping variables. Now we've seen class statements before in PROC means and some other places. A class variable is typically what we call a classification variable or a grouping variable, like 1, 2, 3, ABC. The model statement that we saw looks very similar to what we saw in PROC Reg. Indicates a dependent variable and 1 or more independent variables. And the means statement is used to define some post hoc multiple comparisons. We'll see examples of these as we move along. All right, here are some common options for PROC ANOVA and PROC GLM for performing a one-way ANOVA or simple repeated measures analysis. The data statement we've seen all the time. The no print we've seen often. It suppresses the output if we want to output the data for some other reason. And to do that, we would use outstat equal a data name, which outputs a data set and saves a number of the results of the ANOVA calculation. Plots equal options specifies what plots to do. Plots equal none suppresses the plots that are normally generated by PROC ANOVA. Order equal option is similar to what we saw in PROC Freak, specifies the order in which to display the class variable. And alpha equal p, we've seen that, specifies the alpha level for a confidence limit or confidence interval. Continued here, we have the class statement, which is required and specifies the grouping variables for the analysis. The model specification specifies the dependent and independent variables and looks very similar to what we saw in PROC Reg. The freak statement, freq and then var, specifies that a variable represents the count of values. And we've seen this again in a number of previous procedures, where if we have the counts of value of certain things, we would use this freq statement to indicate which variable contained that count or weight for the particular variable. The means option calculates the mean for dependent variables and may include some comparisons. We're going to see this. Similarly with LSMEANS, we're going to have what we call least square means for a dependent variable. That's used in PROC GLM. Repeated measures specifies repeated measure variables, and again we're going to see examples of these. But test specification is used when we want to specify a hypothesized test value. A contrast statement allows us to create customized post hoc comparisons, again for GLM, and then the by format label and where statement that we've seen before. Okay, let's look at using the means or LSMEANS statement. So when we perform a one-way ANOVA, there's typically a two-step procedure. The first step is to test the null hypothesis to determine whether any significant differences exist. That is, the null hypothesis is that all the means are equal. Well, if we reject that null hypothesis, then what do we do? That's step 2. If the null hypothesis is rejected, we could run subsequent multiple comparison tests to determine which differences are significantly different. In other words, which means are different from one another. Pairwise comparisons of means can be performed using one of several techniques specified in the means statement, which is the following format, where the independent variable is a class variable. So here we have means and then some independent variable slash whatever type comparison we want to do and some options. Or for PROC GLM, we use the LSMEANS statement. Similar, everything is similar except we're saying LSMEANS, least square means, rather than just means. So let's look at some common type comparison options for PROC ANOVA or GLM. So you may have heard of some of these, but here we have the Bonferroni, which is the option BON, or Duncan or Chaffee, Student Newman-Cools, the Fisher's least significant difference, the Tukey test, the Dunnett test, and we can also specify the alpha level for these comparisons, and also request that confidence limits be included in the output. So continued here with table 14.2, so some common type comparison options for the PROC GLM LSMEANS statement. These are options following the slash. We could have a just equal option to specify the type of multiple comparison. And again, examples would be Bonferroni, Duncan, Chaffee, and so forth. Or pdiff equal, which calculates p-value base. The default is the t, but we can also specify Tukey or Dunnett options here. All right, so let's look at some examples. This is example 14.1. Open up the file called ANOVA1.sas. In this case, we have PROC ANOVA from some data that we have called ache, toothaches, and or headaches, I think. And so we specify the class, brand. That's the brand of medicine that's taken to relieve the headache. So it has at least 3 options there. We have the model statement. Relief, which is on the left-hand side of the equal statement. Relief is what we're trying to predict, equal brand. So we're trying to say, if I know what brand of headache relief medicine I take, can I predict what kind of relief I'm going to get? So again, the similar model statement to the PROC reg, except in this case, brand is a grouping variable. So if I know what brand, can I predict relief? And then we're going to have this mean statement, which we're going to use to do post hoc tests. So if the null hypothesis is rejected, then this means option is going to allow us to determine which means are different. All right, so when we run that program, we're going to get this, this table. So notice that the source, or what we're comparing, is brands, and the p-value on the far right, p equal 0.0091, is used to decide whether or not to reject the null hypothesis that all means are equal. So typically, if less than 0.05, we reject it. So in this case, we do reject the null hypothesis, and indicates that some mean, one of these, or two of these headache medicines are different. Now let's look at what the means statement did to produce some post hoc results. All right, so this sort of depends on what SAS version you're using. You may get a slightly different version of the Tukey grouping here, but this is probably the more recent one. So this is the grouping using the Tukey comparisons. Now notice what we have here. In this graph, the mean for brand 2, which is 30.88, sort of stands alone. You notice it's in a blue color, but the means for brand 1 and 3, 28.5 and 26.2, notice that they're sort of combined now with this red bar. So what this is saying is that the red bar says these two means are considered equal or not different, and the blue bar, or the different bar, says that brand 2, 30.88, is different than the other two. So if our estimate is time, then we could say that headache medicine 2 took longest, 30.88 minutes or minutes probably, but there was no real difference between no significant difference, a statistically significant difference between brands 1 and 3. All right, here's another way to look at this table. Again, we have the Tukey grouping on the left, and we see in this case it shows that the Tukey grouping A for brand 2, again, it sort of stands alone, whereas the BBB down there sort of groups the other two brands 3 and 1 together, saying that they are not different. Different ways to come to the same conclusion. Again, a third way to look at this, so this graph reinforces the statistical results. Notice that groups 1 and 3 are very similar. Their boxes overlap quite a bit. However, the box plot for brand 2 stands above the rest of them and is separated, and that again gives us some visual confirmation that brand 2 relief takes longer than brands 1 or 3. All right, so let's use this code for the comparison test as an example of something different. So we say means brand / Tukey CLD diff. In this table, mean differences are compared. For example, the first line tests the difference between means for group 2 minus 3. So we see so we're comparing 2 versus 3, and the difference is 4.3. And then the little star indicates a significant difference. So we can see that 2 is different than 3, 2 is different than 1, 3 is different than 2, 1 is different than 2. There's some of them are, obviously just the opposite of one another. But 3 and 1 are not different, and 1 and 3 are not different. So we come to the same conclusion in just a different way, that brands 1 and 3 are not different, but everything is different than from brand 2. All right, if we use PROC GLM, we just go in there and change the word ANOVA to GLM and use the LSMEAN option, LSMEAN brand / PDiff, we get this table. So this table reports the results of mean comparisons. For example, the comparison of mean 1 versus 3. So if you look at 1 versus 3, you get this 8.524, indicating the difference in means is not significantly different. This is a p-value that's being reported here. However, the difference between 2 and 3, means 2 and 3, 0.0080, is statistically different. So again, we're just using different ways of comparing two means at a time. And why are there so many? One reason is because there's so many different disciplines that use statistics. And so if you're doing psychology, you may be using or commonly use different methods than engineers use and medical researchers use. And so sometimes it just really depends on what is acceptable in your line of work and your discipline as to which one might be the one you would use. There are other theoretical reasons why you would use one over the other two, but we don't have time to go into that. All right, so let's look at section 14.2, comparing 3 or more repeated measures. Now, this is going to be a different concept than what we were just looking at. So repeated measures are observations taken from the same or related subjects over time or in different circumstances. So in the previous section, when we had means, they were from 3 or more independent groups. That is, group A, B, and C contain different people, or different subjects or different entities, whatever it was. They're completely independent. So whoever was in group 1 was not in group 2, was not in group 3. However, in a repeated measure, we're going to take subject 1 and observe them maybe 3 times. Or maybe they're related in some way. We've matched them in some way, but they're observed more than 2 times. So when there are 3 or more repeated measures, the corresponding analysis is a repeated measures ANOVA. It's a different kind of analysis, as we're going to see. So the hypotheses are, the null hypothesis is that there is no difference among the group means. In other words, there's no difference in the means across the time or the differences that we've measured it. So if we're measuring time 1, time 2, time 3, we're saying that there's no difference in our observed means between time 1, 2, and 3. Or the alternative hypothesis is that there is a difference. Maybe the first mean is low and it gets higher and higher, something like that. Okay, let's look at a hands-on example of 14.1. Open up the program file named ANOVA1.SAS and you'll see this code. Now, we've seen the PROC ANOVA code in general, but let's look at these 3 in particular statements here. First of all, we have the class statement, class brand, and that defines the grouping variable brand. Now, by grouping variable, we mean that it's like 1, 2, 3, ABC. In this case, it's headache medicine, so it could be Advil, Tylenol, aspirin, or something like that. Whatever classification variable it wants to be. And then we have a model statement, very similar to what we saw in a regression model, where we want to predict relief if we know brand. So if we know the brand, we want to know, can we predict what the relief is? One of the big differences between PROC ANOVA and PROC reg is brand, in this case, instead of a continuous variable, it is a categorical variable, as we see. And then also, once we test the null hypothesis that there is no difference between brands, if we reject that hypothesis and say there is a difference, then the means statement, in this case with the Tukey comparison, will allow us to make those comparisons. So initially we get this table, the one-way ANOVA results here. And notice that brand is the source. That means whatever we're testing. Degrees of freedom is 2 because there's 3 brands in this particular analysis. And we see that the p-value given is 0.0091. That's less than 0.05. Therefore, we reject the null hypothesis that the means are all equal, and we have evidence for the alternative hypothesis that there's at least some difference in the means. So we're going to look at a variety of ways that SAS allows us to look at that information. The first one here is a Tukey grouping for the means of brand. And so on the left we see the brands 2, 3, and 1, they're ranked in order, highest to lowest. And then we have the means as the estimate. And then we have these bars. Now what the bars do is they try to group the brands according to which ones are different. So brand 2 is a blue bar, it stands alone. What that means is that group 2, the 30.88, is statistically significant or higher than the other ones, the other means. And then groups or brands 3 and 1, 26.5 and 26.2, with the solid red bar sort of grouping them together indicates that they are not different, again at the 0.05 level. Another way to look at that is with a table, and basically we have the same thing here where we have the Tukey grouping. Notice A for brand 2 separates it by itself. There's a blank row there. And then we have the B group, which is the other 2 groups, and that's group 3 and 1, and they are again grouped together. So we see that A is significantly higher, whereas our brand 2 is significantly higher, whereas brand 3 and 1 are not different from one another. Another way to look at that is with a bar chart. Box and whiskers chart. So here we see brands 1 and 3. The box and whiskers plots are overlapping, and they're down toward the lower end of the scale there of relief, and then brand 2 is higher, and we can visually see now that brand 2 resulted in a higher mean, higher overall than the other two brands. Again, it's very important to look at graphs when you're doing some sort of comparison. Instead of just looking at the p-value, it's very helpful to look at a graph and try to visualize what's going on so that you're not confused by maybe what null hypothesis you were testing or something like that. The p-value can be misleading, and so we need to back that up with some graphs, and that's what we're doing here. Again, here's another way to look at it. If we have the statement means brand / Tukey CLD difference, that's going to give us some simultaneous 95% confidence limits on the difference between the means. And here we're going to compare every pairwise comparison. So here we have on the left brand comparison 2 to 3, 2 to 1, 3 to 2, and so forth. And then if we go to the far right, we see the little 3 stars there. That indicates a significant difference, again at the 0.05 level in this case. So we see that it's the same results, but just displayed in a different manner. Now, if we were using PROC GLM instead of PROC ANOVA, in fact, we can just replace GLM with ANOVA, ANOVA with GLM, and change the mean statement to an LSMEANS brand / PDIF. Then we get this least squares means difference that we can test here. And again, this is a table, and what it's doing here is we're comparing, for instance, group 1 to 3, and then this is the p-value. Are they different? 0.85 as a p-value? No, they're not different. However, 1 compared to 2, 0.0056, that's lower than 0.5, and so again, we can do any pairwise comparison we want using this table. Again, we get the same results as the rest of them. Why are there different ways to do it? A lot of this came about because there are different disciplines that came up with these various tests. Maybe some were engineering and psychology and medical science, all these different kinds of ways of looking at the same thing. That's one reason. There are some theoretical reasons for these differences as well. All right, let's look at section 4.2, comparing 3 or more repeated measures. Now, previously, we've been looking at groups where we had the 3 groups of medicines, and in each group there was different people in each group. So that was called an independent group comparison. Whereas a repeated measure comparison, we take one person and we observe them over time or in different circumstances. And so that's what a repeated measure is. So it's very easy to, if you're not careful, to get confused about which tests to use. But just look at where the means are coming from. Are they from independent samples where in each group there are different individuals or entities, or is it the same person or group or whatever being observed more than once? Then that would be a repeated measure. So when there are 3 or more repeated measures, the corresponding analysis is a repeated measures ANOVA. And the null hypothesis is that there's no difference among the group means in the repeated measures, or alternatively, there is a difference between the group means. All right, so here's some code that we would use to do that. We say PROC GLM. We're going to use the data called study. In this case, what we're looking at is the same individual was given 4 different drugs over time. We're going to see the data for that in just a minute. But so with our class statement, what we're wanting to know is there a difference between the drugs? And so drug is one of the classification variables there. Now, in this case, subject is also listed as one of the classification variables, and it's in there for reasons for the model, even though we're not really interested in if there is a subject difference. So just be aware that in this case, it's in there, but it's of no analysis consequence. So similarly, in the model, we have result. We want to know, can we predict the result knowing what drug someone was given? And again, we have the subject in there as an important part of the equation. And then finally, if we reject the null hypothesis that there is no drug difference, and so we have evidence that there is a drug difference, we can use the mean statement to compare drugs. And in this case, we're going to use the Duncan comparison. All right, let's look at what the data look like then. So here you see we have 5 subjects, and each subject was given 4 different drugs. Now, they weren't given them sequentially, because then we might have a sequential aspect to our analysis, but they were given them in random order. And there are ways to do that sort of beyond what we're going to talk about here, but we would randomly assign how they would get the drug. So subject 1 may get drug 1, 2, 3, and 4, and then 2 may get 2, 3, 1, and 4, and so forth, in sort of a random fashion there. All right, and then we have to know how to put that data into SAS. And if you open up the program file AGLM1, at the top of it you're going to see data study, and notice we're inputting subject, drug, and result. So unlike most data sets that we've seen, where a single subject would be on one line, all the data for a subject would be on one line, this is different. We have the same subject, 1, 2, in 4 different lines. And so notice that at the far left, that's the subject variable, 1, 1, 1, 1. It's all the same subject. And then the next one is which drug they got, 1, 2, 3, 4. And then the results of whatever the test was is the data there. So again, just pay attention to the fact that it's quite a bit different how this data are set up. These data are set up so that we can run this analysis. All right, so once we have the data set called study, then we can do PROC GLM, class against subject drug, and then the model, same as we saw before, result equals subject and drug, and then the means. If we want to do multiple comparisons, then in this case we're going to do the Duncan comparison. So we run that analysis, that program, and we get this initial table. And notice this is the type 3 table. There may be other tables that are displayed. In this case, make sure you're looking at the type 3. Notice at the top it says type 3 SS, type 3 sums of squares. That's the appropriate table that you need to look at to do this analysis. It has the subject line. We're not interested in if there's a difference between subjects. We assume there is. But we are interested in the drug line. The drug, again, a degrees of freedom of 3 because there's 4 drugs. We get a p-value less than 0.05. So we have evidence to reject the null hypothesis and conclude that there is evidence that there is a difference between drugs. All right, again, we get in this case we ask for the Duncan comparison. It looks very similar to the Tukey comparison, where we have this the drug listed over on the left, 4, 1, 2, 3 in order of the size of the mean, where they have estimates 33, 26, 25, and 16. And then the bars are separating the groups according to whether or not they are statistically significantly different, or if they're not different. In this case, drug 4 is significantly higher at 33 than the rest. Drugs 1 and 2 are not different at 26 and 25, and drug 3 is significantly less at 16.6. And some versions of SAS may output this table, and again, it's basically the same information. As you can see, we have the Duncan grouping where it has A, B, C groups, and it groups them into how it believes that the results of the test to determine what values are different and what are not. One that I like is this graph here, and you can see what this does is, let's look at the green line. The green line is subject 3. The green line is drug 3, And we can see that the drug 3 is consistently less than all the other values over subjects. So every subject's value is lower than the results of the other observations. However, the blue and the red line, which is groups 1 and 2, or drugs 1 and 2, are very close together. So we're going to conclude that those two drugs are virtually equivalent and are not showing any difference. However, the black or brown line there, drug 4, is higher than all of them consistently. And so that, again, is a visual confirmation of what we've seen in the other graphs and in the tables. And again, it's a great idea to look at the graphs to visualize what's actually going on so that you can determine whether or not you're understanding the results of the analysis. All right, so let's use, we used the means statement, but let's use the least squares means statement, which we need to use for the PDIF. So LSMEANS drug PDIF adjustment we're going to use is Tukey. Now in this case, we're again doing a pairwise comparison. So if we want to compare drug 1 and 2, we get a 9.966 as a p-value. Well, then 1 and 2 are not statistically significant, or not different. However, 1 and 3 at 0.0005, 1 and 3 are different. And so this table allows us to do specific pairwise comparisons of any pair of drugs that we're interested in. You might also then do the other options like Bonferroni, Dunnett, and Chaffee. You should get pretty much the same answers, but it's a good exercise to do all of them. Again, why are there different ones? But again, it could be a theoretical difference, or it could be simply that different disciplines came up with different ways to do this. Okay, let's look at section 14.3, going deeper, contrast. So up to this point, when we did an analysis of variance, or repeated measures of analysis of variance, the post hoc test compared every possible comparison. But that's not always the case of what we might want to do. At times, we might want to make specific post hoc comparisons. For example, suppose you have a data set consisting of 4 groups. For some hypothesized reason that you created before you collected the data, that's when these should be done, you wonder if the average of means 1 and 2 is different from the mean of 4. You can do that with a contrast statement. And it has the form as we see down here below, where we have contrast, a label, the independent variable, this is our grouping variable, and then effect values, and we'll define what these effect values mean. All right, so for instance, here is a contrast statement where we're going to compare group 1 versus the combined mean of group 3 and 4. So here we have the contrast statement, and then the label we can do whatever we want to there. We're saying 1 versus 3 plus 4. And then we have, here's our definition here of the contrast. So we have group is the independent variable, the classification variable that we're using. And then notice the -1 corresponds to the first item in the group, 1, 2, 3, 4. So -1 corresponds to 1. 2 is not in our contrast at all, so we put a 0 there. And then 0.5 gives half the value each to 3 and 4. So we can define this, other ways to define it. You can see here below, simply we're this -1, 0, 0.5, 0.5, it always adds up to 0. And you can look in the text and get more specific information how to design that, but basically that's the way that you do it. So let's look at a real example here. Open up the program file AGLM contrast, and you'll see this code. So we have PROC GLM data contrast. Our grouping variable is called group, our classification variable. So we have class group. Our model, we're trying to predict observation from group. And we're going to define a specific comparison. Instead of doing a Tukey comparison or something like that, we're going to define a specific one. We're going to compare groups 1 versus the combined 3 and 4. And notice here we have group, that's our independent variable. And here are our contrast values, -1 corresponding to group 1, 0 corresponding to group 2 because it's not in the contrast, and then 0.5, 0.5 for 3 and 4 because we're going to combine those and again add all that up and it adds to 0. So here are the results of this analysis. The first table gives us the overall type 3 sums of squares comparison where p-value is less than 0.05. So this would reject the null hypothesis that all the means are equal. But instead of doing multiple comparisons, we're going to just do this contrast where we have groups 1 versus 3 and 4. And again, we get a p-value less than 0.05. And so here is evidence that groups 1 versus the combination of 3 and 4 is statistically different. All right, so here we could add some more statements. So I've added 2 here. Actually, the first one is really the same as the one we just looked at. I've just changed the number values. So instead of -1 and 0.5, 0.5, I put -2 and then 1, 1. It still adds up to 0, and it still gives me the same contrast as you can see in the table below. Or the second one there is 1 and 2 versus 3 and 4. And in this case, I have -0.5, -0.5, and then 0.5, 0.5. Again, it all adds up to 0. So you can see in the table below, the first two have identical results because they're basically identical contrast. Just wanted to show you that you could do it. There's no secret to choosing the values in that sequence of values to add up to 0. And then the last one there, again, comparing 1 and 2 versus 3 and 4. Again, the p-value is less than 0.05. So we would say that there is statistical evidence that combination or that comparison is statistically different. All right. Well, that summarizes, or this is the end of chapter 14, where we looked at independent group and repeated measures analysis of variance. Our next chapter is going to be chapter 15. It's really a part 2 of analysis of variance, going deeper into how to do an analysis of variance using some additional kinds of models. So if this was helpful to you, we appreciate you liking and subscribing to this channel, and we will see you next time. Thanks.